G'day there, you're watching the Aussie BIM Guru. Today I've got an exciting video where I'm going to show you how to build an adaptive tensile shade, but we're going to use Rhino Inside to guide the placement of the adaptive component. So it's quite an interesting little workflow, essentially creating something that might look a little bit like this, but we're going to enable for both tension on the edges and sag in the middle as well. So previously we used just purely adaptive components to place such an element, and we just used basic parameters to control the tension and the sag. So whilst this might be semi-accurate in terms of representing tension and sag, it's not really related to a physics-based test, but we can actually introduce some physics to this as well. To do this, we're going to have to use Rhino 3D, or more specifically Rhino Inside. So you are going to need access to Rhino Inside, which if you are a Rhino 6 user, is available to you. I believe you can also use it on the Rhino Beta as well, or the Rhino Trial. As well as this, you'll also need the Kangaroo solver. This does come with Rhino 6 and also Rhino Work in Progress, which is where we run Rhino Inside through. So we are going to be running Rhino or Kangaroo inside Rhino, or Kangaroo inside Grasshopper, inside Rhino, inside Revit. So it's a little bit of a complex workflow, but I think it's a good one to show you how to use Kangaroo as well to solve physics. So let's dive right in. So I'm in the model I actually used for my previous video. In this case, this is the destination we're heading towards. So a 4-point adaptive shade with a sag point indicated as well. So I am quickly going to build this component as well, just to show you how this adaptive component comes together. So to do this, I'm just going to go New Family. I'm going to go find the Metric Generic Model Adaptive Component. Now in this case, I believe I was just going around the edge. So 1, 2, 3, 4, 5. Yes, so I go around the edge, and then the last point is in the middle. So I'm just going to place a set of points, and in this case, I'll make them adaptive after I've placed them. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So notice I was being really rough there. It doesn't matter if they're not placed perfectly. I'm going to make these parametric just by deselecting this reference plane. So make adaptive, sorry. And then I just need to create 3 reference lines through them, or 3 splines through them, which I'll then convert into reference lines. And if you do want to see these techniques in a little bit more detail, probably refer to my Revit video. It's a little bit more deep on adaptive components. From there, I'm just going to connect these with a create form, and this will just loft a form through there, which will allow for a 9-point adaptive surface, essentially allowing us to create a tensile or sagging element in Revit. So at this point, I'm just going to just do a quick purge, a save as, and just save this as a family I can work with. I'll call this new shade, and I'll load this into my model. So I am going to delete my initial shade. Now what I have here is I have 4 1-point adaptive components. Now to build one of these, it's quite easy. All you have to do is go New Family, and again, we're going to make an adaptive component. And these are really just like anchor points to guide Rhino Inside for where to hang the shade from. So in this case, you could work with more than one placement point to hang this component from, as long as your adaptive component is built, I guess, to build up the framework of this element. But in this case, I can just place a point anywhere, make it adaptive, draw a circle at this point, and I'll just make this a nominal radius and make sure I'm drawing at the point. I'll make it 300, and in this case I'll just call this new anchor. And because it's a 1-point adaptive component, it's actually quite easy to place this element. I believe I called this new anchor instead of anchor, but that's all right. So if I just go to place a component, I'll be prompted to place the last component I loaded, and I'm just going to place these on face, and I should be able to get these vertex snaps. And notice I can just place these on the corners, so this is going to give me the perfect way to guide Rhino Inside for where these points should be. So in this case, I'm going to have to boot up Rhino Inside. So in this case, I'll just open up Rhino Whip, and now I'm in Rhino Whip, and I also have Grasshopper available as well. So this is all running inside Revit. I do have some videos on Rhino Inside if you're interested in finding more out about just the fundamentals. But in this case, I'm just going to jump straight into Rhino. So what we're going to do first of all is actually collect our anchors. So I'm probably going to need to actually make this just a little bit smaller to keep it out of the way. And in this case, I'm just going to get a model categories picker. I might also just get a little pair of bifocals so you can see what the names of the nodes are as I place them. And I am going to be collecting generic models. From this, I want to get an element type picker. So in this case, I'll just look for element type picker. And if we connect this up to a Revit category, this will allow us to pick an element type from that list of category elements. So now I can see I can access my shade or my anchor. In this case, I'm going to pick my anchor because I want to collect all those 4 anchors from my model. From here, we have to build up a filter. So I believe filters are located under the Revit tab, filter. And in this case, we want to use a element type filter as well. So I'll just get this type filter. And now that we've got our type filter, we need to query the elements from our model. So in this case, I'm just going to make sure I use the right family, which is actually new anchor. This should apply the filter to all elements in the model. And I can see now I have my 4 instances of new anchor. From here, I can obtain the element's geometry. So in this case, I'm just going to use the element geometry node. And at the moment, I'm going to have the 4 circles that I placed into my adaptive component. Now in this case, I can actually just connect these to an area node, which will find the centroid of these circles because it's the only geometry in my component. So this is quite convenient for me to just collect these little anchor points as actual points. I might also just flatten my input in this case, so I get these just all as 4 points altogether. From here, I'm going to generate a polyline by point. So in this case, I'm just going to make a polyline from these centroids, and I am going to need to connect the endpoint as well. So I'm going to set this to true. Now I have just a four curve framework for my shade, which I'm then going to convert to a surface. Now at this point, I do need to rebuild this surface, and I find that when I'm using Rhino with this workflow, it's much easier to take this geometry into Rhino itself and work with it locally. So at that point, I right click on this and bake. And then I usually take this surface and I just type in rebuild in Rhino itself. I can then divide this into a nominal number of U and V divisions. In this case, I'm just going to specify 25 by 25. And this gives me a lot more sample points to play with when I analyze this geometry in Kangaroo. So at this point, I'm just going to hide a few things in the start of this workflow, just so we can just see our native surface, which is now in Rhino. So we're not really relying on the Rhino Inside connection at this point, so it's a little bit faster to work with. So what we'll do now is just go and collect a surface. So I'm just going to set one surface by right-clicking on this node. Now I have this surface in Grasshopper. And I'm also going to convert this surface to a mesh. So I'm going to connect this to a mesh node. Now the reason I'm doing that is because Kangaroo has to solve using mesh geometry. I'm also going to turn off these 2 previews. And then I'm going to begin just building a few things that I'll need in order to work with in Kangaroo. So at this point, I do need to build a few goals to solve in the Kangaroo solver. I might just give myself a little bit more space here. So the first goal I'm going to have in Kangaroo is just to show what I'm doing. So I'm going to get the show goal in this case. And this will just show the preview of what's happening in Kangaroo itself. So it's not really a goal, it's just a goal of what the solver has to do for us. As well as this, I'm going to apply some vertex loads. Now I'm just going to check where this one's located. It's a vertex load goal under, in this case, goals mesh vertex loads. So in this case, I'll be taking my input mesh and applying a strength. Now typically I work between -3 and 3 for this particular workflow, so I'm just going to make a slider. I'm going to go from -3 up to 0 up to 3. So to begin with, my goal will be set to 0, so there'll be no vertex load placed on this element for now. But what we're also going to do is also create a goal for the edge lengths to create some tension along the edge of this as well. So I'm just going to look for edge lengths. And again, we'll just have a look at where this goal is located. I believe it's also under mesh. Yeah, so we can see it's there under goals mesh. Again, we're going to take our input mesh. And in this case, we work to what's called a length factor. So this is how taut the length edge should become based on a factor of 0 to 1. So in this case, I'm going to go from 0. And I'm going to start at 0.7 up to 1 with the length factor. As well as this, we also need to establish some anchor points for the corners of our mesh so that it doesn't just compress entirely. It does need to stay taut on the anchor points. So in this case, I am going to call on a mesh corners node. In this case, just a standard mesh corners node, I believe. Yeah, there we go, mesh corners. So I'm going to take my input mesh, which will identify the 4 corners of my mesh. And then I'm going to establish an anchor goal. So in this case, it's called anchor. In this case, it's located under goals point. So I'm going to take those points in this case and just work with the default values. So now I can collect these into a Kangaroo solver. So in this case, I'm just going to take a standard solver component, I believe. Yep. And I'm just going to connect all these goals together. So I'm going to have to hold down, I believe I might have to hold down Shift in order to collate these goals together. Yep, so if you hold down Shift, it supports multiple goals. Notice that things are already happening. So on this point, we have no anchors. Now we have anchors. So see that each of those goals has an impact on how the study behaves. So it's pretty cool what happens with Kangaroo. Now we do need a way to stop this solving because it's constantly solving at the moment. We do need to create just a toggle, and we'll just use a Boolean toggle, just to make sure that we have control over when our study runs. I'm also going to add a button as well, so we can reset our study as well. So I'll connect that to the reset. So now if I reset, whilst the toggle is set to false, nothing happens. As soon as I turn this toggle, my physics starts running. Now I can start doing some more interesting things. I can start changing the amount of tension I'm exerting on the edge by changing my length factor on my edge lengths node. I can also start applying load to the vertices to start draping my canopy. So pretty cool, right? So you can see some really interesting impacts. You can even apply negative tension to elevate. So if you have like a wind force coming underneath. Now there actually are ways to put wind onto the canopy as well. I'm not going to do them in this case, but definitely explore this package because there are so many ways you can solve physics. You can do explosions. There's all sorts of crazy things that Kangaroo can do. Very fun package. I'll probably cover it in more detail in some future videos. But for now, I'm quite happy with this. So I'm just going to toggle this just to maintain the state of the current canopy position. Now we can see Kangaroo is done. So at this point, we do need to work with the output. So we do get a few things in our output. Let's just check what we're looking at. We've got a mesh, and we got a whole bunch of nulls at the moment, but we have some lines as well. I assume these might be the lines of the mesh itself, but we're just going to work with the mesh. So I do need to call on the list item of the mesh. So I'm going to get a list item node, and I'm just taking the item at index 0. So I can just use the default value in this case, and I'll be left with my mesh if I work here. Now I'm just in this case going to flatten my input so that I only get the first item of the entire set of objects. Otherwise you'll get the first item of the mesh list and the first item of the second list. Now I'm just getting my mesh. In this case, I can actually just probably stop previewing that mesh because I already have a copy of it from Kangaroo. And we're going to have to do a few other things now as well. We are going to have to find a center point of that mesh as well. So to do this, I'm going to go back and take my original surface. Now, first of all, I'm going to find the middle of that surface, just using an area node, just to find the centroid of my base surface that I generated my mesh from. Now, I might just move this down a little bit just to make some room. I'm also going to have to evaluate a surface at a certain point. I believe I may not necessarily need that actually. I do need to evaluate the surface because I need to find the normal at the center of the surface as well. So I'm just going to get an evaluate surface. And I'm going to evaluate my original surface. I may not actually need this point. I think this will generate me a point as well as a normal, yeah. So I don't need this node actually. I'm just going to work with a surface evaluation. I'm going to construct a point now, and I'm just going to specify the X and the Y values as 0.5. So I get the absolute center point of my surface, but I also get the normal at that point as well. Now, in this case, it's interesting. It looks like it's assessing, doesn't look like it's assessing this quite how I want to. Oh, I need to reparameterize my surface. That's why. So I'm going to reparameterize my surface input, and that should hopefully work. Oh, okay, I've connected that wrong. So it needs to be 0.5 for Y, for X and Y. There we go. Now I have that point, and I can also extrapolate the normal as well. So I'm going to just type in SDL to get a line by start direction length. I'm going to start at the point by the normal, and I'm just going to move by just a nominal distance, maybe like negative 5,000 for 5 meters. And in this case, I might need to work the other way. So I'm going to go 5,000 instead, because I just want to intersect my resultant mesh that I generate. So in this case, this will give me a curve that I can then intersect with my mesh from my study. So in this case, I'm just going to take a mesh curve intersection. And I'm going to take my final mesh and that curve, just to find where I intersect this mesh surface, just so I know where that 9th point is in my adaptive component when I place it. So I can probably turn off a few of these previews now, just to make everything a little bit more simple. I may be able to even turn off Kangaroo potentially. I'll keep it on for now, because Kangaroo is probably the best thing to see. And now I can start analyzing my resultant mesh, and I really want to just find those points to place my adaptive component by. So I can, in this case, just take another mesh corners node to find the corners of my resultant mesh. And that will really just give me my 4 vertex load points. I'm then also going to do a few little complicated things just to make sure that I get the absolute points. So I'm going to do a mesh edges with tolerance. And I'm going to take my base mesh. And in this case, this should give me the perimeter curves. And I'm really just doing this so I can find the point midway along this curve to place my adaptive component. So I'm also, in this case, just going to turn off this preview. And I'm going to join these curves into a single result. And I'm really just doing this from the naked curves, so that I can get these in a logical order to make sure that I can actually shatter these in a logical way. Now I'm also going to find the closest point from each of the mesh corners to this curve. In this case, I may need to take something a little bit different here. Probably need to, actually I think in this case, I've got 4 corners and I've got a polyline curve. I think it needs to be a curve closest point. Yes, curve closest point. So I'll take my point and my curve. And now I'll find the closest point that's exactly on those curves as well. What I can do then is just shatter at those points. So I'm going to break that curve at each of those corners. And this will ensure that I get each of those segments in a clockwise order, ordered from the first point onwards. So now I'll have the ability to find the next point along each of those curves and reconstruct them in a logical order. So in this case, I'm just going to take this as the point and this as the curve. And I should end up with curves at those points. So in this case, I'll have 4 curves and they should be ordered around my result. I can then take a point on curve node, which should be a slider. And in this case, I'm going to do it twice. So I'm going to take 1 point at 0 of each polyline curve and 1 halfway along. So this should give me the midpoint of each corner and also the start of each corner as well. And these will be in an order that I can reconstruct them around the surface in an order that suits my adaptive component. So I'm going to put these back together using a merge node, and I'm going to merge those 2 lists of points. Now I'm going to do this in a slightly different way. I'm actually in this case going to graft these across each other so that I'm adding the first item of each list together. So I'm getting the first item, then the first one at 0.5, then the next one on the curve, then the next one at 0.5. So I'm sort of inverting my list or transposing it at levels. But I'm then going to merge this again. So I'm going to take these points, and on the end of that entire list, I'm going to take my resultant intersection point from my mesh curve intersection. Now I'm going to take a flattened output here so that I just get my 9 points in this case. And these are my 9 points for my adaptive component. So it's a little bit of a complicated list management exercise, but we got there in the end. So list management in Grasshopper can be a little bit more challenging than I find in Dynamo. It did take me a little while to figure out how to put this data together in the order I needed it. But in this case, we're going to be aiming for a Rhino Inside node in this case. So we are going to be placing an adaptive component. So I'll just search for adaptive component in this case. I believe it's add adaptive component is probably what we're looking for. Add component adaptive, which should be under Revit, under build. So in this case, given a collection of points, we're going to generate an adaptive component. So I'm just going to connect in this case the adaptive points. Now obviously we don't have a family type yet in order to guide this. Now I like to usually feed this into a stream filter. A stream filter will essentially block data until a Boolean gate is true. So in this case, I'm going to set my true gate, or my 0 gate to nothing, and my one gate to the family type. So I'm going to take a button so that I can only really send through this family type once, so that I create the element once. So when I press this, notice that stream 1 becomes the input. So if I just click this, I send through the data once, which will create one family. I'm then just going to also get a model categories picker again. In this case, generic models is again what I want. I'm going to get an element types picker. And now I'm going to be picking my adaptive shade instead. So I'll just drop this down and I'll get my new shade. I'll put this into my one gate. And now when I run this, I should get the adaptive component in Revit. So I might need to lay out my tabs so I can really see what's going on. I'm just in this case going to move Revit over here and just try to arrange it so I can see a few things at once. I might just make Grasshopper just a little bit smaller. But we can now see that our input is ready. That's the preview geometry of Rhino Inside. If I run this, I should get my adaptive component, hopefully. So one step I missed that is important is we do need to flatten the output of our list of 8 points before we add the other one. In this case, this should put our points in the correct order to generate an adaptive component. So at this point, if I do run my node, we can see now we successfully place an adaptive component. Now it may not perfectly match the output from Kangaroo, but it should very closely at least capture most of that shape. It's mostly related to how the Kangaroo physics differs in how accurate it is versus an adaptive component. Now you could introduce more points, more profiles to really capture the precise geometry of this output. In this case, we've sort of approximated it around those anchor points. You can see that there's a little bit of discrepancy here, just because the tautness isn't captured in a simple 9-point adaptive component. You'd probably need this to be maybe like a 4x4 or a 5x5 surface. Obviously, this takes a lot more time to set up, and it can be harder to order the results of using Grasshopper itself. But we can see in this case, this also gives us the ability to go and sort of change the condition that we're using in our study. So I can always start my Kangaroo solver and change some conditions. Let's say we want to do a set in the other direction. I can also change my edge lengths, stop my solver, go back to the end of my script and just run my script, and we should be able to run this in the other direction. In this case, it appears maybe I might have given it something a little bit too extreme to work with. Probably these edges might be just a little bit too taut. So I might just try lightening those just a little bit instead. We'll try that. Or maybe it's just the adaptive component doesn't work well in the inverted direction. That could possibly be the cause as well. But there are going to be some limitations in how you need to tailor your adaptive component in order to generate your result. It seems like in this case, if it's inverted, it's not happy. So you may need to play with the surface normal direction of your surface as well, depending on how you set up your canopy. Now in this case, I could actually add more points. Obviously my adaptive family isn't built to handle more than 4 points, but just for testing's sake, let's just have a look at how we could just play a little bit more with what we're dealing with. So in this case, I might just copy this over here and just try creating a different set of points instead. So in this case, I'll just recollect all my input points back at the start. Remember, we have to generate the original surface first. So in this case, we should be able to collect all of these, hopefully. Delete my original surface. Now in this case, it appears maybe my order I've placed these needs to be different. So you do usually need to place these in a logical order to generate the original polycurve. So I'll go 1, 2, 3, 4, 5, 6. I'll try now, and hopefully this should be an order that supports a valid polycurve. I'll just have a look at what this polycurve looks like. In this case, it's not happy generating a surface, obviously because I guess it's an undulated surface. I could try patching the surface instead, which might cause some challenges. It appears that that at least is an option for generating our surface instead. And I believe I should be able to bake this into Rhino. And then rebuild 25 by 25. And I'll see if we can work with this using Kangaroo instead. I'm not sure if we can. I'm just sort of experimenting here. I haven't actually tried this, but it'd be pretty interesting if this does actually work in Kangaroo as well. It looks like it does. That's pretty cool. I'm not quite sure if it's going to solve itself, but let's have a look. Oh wow, there you go. So you can see that Kangaroo can pretty much work with similar solving conditions. It didn't find all the anchor points, probably because of where it interprets the mesh corners. So in this case, it misses a mesh corner here. So you may need to work with some different ways of collecting these anchor points. But in this case, it does at least look like we have managed to collect a majority of our study and work with it in Kangaroo. But yeah, you can see there are some issues in how meshes interpret their corners. But yeah, definitely have a play with Kangaroo and see if you can find different types of shades that you might be able to generate using a similar type of study. And I hope you found this an interesting way to look at using a different medium to generate a Revit-based solution, even if a little bit more complex. Obviously, it does some things that Revit can't do itself. Anyway, that's all for this presentation. So the files for this will be on GitHub, as usual. And I look forward to seeing you in future videos. If you're not already following and subscribing, feel free to do so. I aim to upload videos 2 times a week, and I look forward to seeing you in more in future. Thanks. Take care. Bye.